Okay, so today we want to start by looking at our next section that we're going to be talking about, which is kind of a big one. It's got a lot of three key ideas. One is inverse functions and how they're derivative, to finding their derivatives and how they're related to one another. In other words, the derivative of one function and the derivative of its inverse function. We're going to be tackling derivatives of exponential functions, which will actually be pretty straightforward and pretty easy. And then lastly, what are inverse trig functions, what their derivatives look like. So that's like inverse sine, inverse cosine. So we might want to break this up into three separate little concepts. So we're going to first focus on inverse functions. So everybody should remember what it takes for two functions to be inverses of one another. Basically, if f and g, as I talk about here, are inverse of one another, that means whatever g does to x, when you apply f to that result, you're going to return back to your original value. So in other words, let's say x goes in to the g function, and it comes out as g of x. Well, if you take that number and you plug it into f, it's going to turn it back into whatever x was originally. And the same thing would happen if these roles were reversed. If you put it into f first, it would come out as f of x. And if you put that into g, it's going to come back out as x. So it doesn't matter which order you do it, f of g of x or g of f of x. If f and g are inverses of one another, they're going to return the same thing. So that's just a little review of inverses. A couple of things that come from that. The domain of one function would be the range of its inverse. So in other words, the x values of one would become the y values of the inverse function, and likewise, the y values of the original function would become the x values of its inverse. And lastly, if two functions are inverses, for example, f inverse here and f here, their graphs would be reflections of one another across the line y equals x. So all three of those bullet points should be a nice little review of what you've done before. Here's a nice little idea. We always learned that a function was going to be one-to-one, which means its inverse exists, or it has an inverse, if it passes the horizontal line test. So that's our primary way that we've always checked whether a function has an inverse or not. Now, because we have calculus, we can think about another way that we might be able to discover if a function has an inverse or not. And it's to say if it's always increasing or always decreasing over a particular domain, then it would have an inverse on that domain. So for example, if you think about a function that's always increasing, something like this, if it's always increasing, it's always going up, so it's going to pass the horizontal line test. If a function is not always increasing, for example, let's say it comes up and levels off and starts coming back down, now it starts to decrease, you can see that's where it's going to run into problems, and it's not going to be one-to-one anymore because there's going to be two different x values with the same y value. So that's kind of a cool thing. We're going to work a lot in the next chapter about finding out when functions are increasing or decreasing. But this phrase, monotonic, means strictly increasing or strictly decreasing. So you look at a quick little graph down here, obviously this parabola, and you say, is it one-to-one or is it invertible? And the answer, of course, is no, because it fails the horizontal line test. We can just say fails HLT. Now, that's all well and good, but finding an inverse function, if you're given a function, how do you find its inverse? It's a little summary of the little rules that we have here. First, you're going to write y equals instead of f of x equals. Then everywhere there's an x, put a y. Wherever there's a y, put an x. And then go ahead and rewrite the function, basically rearrange the function and solve for y. And then you can call that new function f inverse. So here's an example of us going to find the inverse of this thing. So we're going to follow our steps. The first thing we're going to do is write, instead of f of x equals, we'll write y equals x over 1 minus x. And then step 2 is we're going to interchange all the x's and y's. So we'd have x equals y over 1 minus y. And now our job is algebraically to get y isolated. And I'm going to go ahead and remind you that this x is like having x over 1 to maybe kickstart you into thinking that we can cross multiply. So if we do, we're going to multiply this way and get x times the quantity 1 minus y is going to be equal to, cross multiplying that way, y. And you may think you're done because you've got y by itself, but you really don't have y by itself because there's another term with y in it right here. So what we're going to do is distribute the x to get x minus xy, and that's equal to y. And now, just like we did in implicit differentiation, everything with a y in it will go to one side, and everything with an x in it will go to another side. So I'm going to leave my x here and say that this is y plus xy. And now, just like we did with implicit, we can factor out the y, and we'll be left with 1 plus x. And now I can divide both sides by 1 plus x. Oops. So x plus 1, same thing. And cancel those guys out, and we get y equals x over 1 plus x. We could just as easily call that f inverse of x is x over 1 plus x. And there we go. So that function that we just created here is the inverse of this one that we put up there. Now, if we were to graph those things, the two graphs would be reflections of each other over the line y equals x. Okay, so that was fairly straightforward to go ahead and find those, find the inverse function. Now, just as a little experiment here, I want to take the derivative of f, and then we're going to take the derivative of its inverse over here, just kind of compare a couple things. First of all, the derivative of f, I'm just going to call it f prime. We're going to do a little quotient rule here. So low d high, so 1 minus x times the derivative of the top, which is 1, minus the top times the derivative of the bottom, which is going to be negative 1, all over 1 minus x quantity squared. Now that numerator is going to simplify to 1 minus x plus x, and then the denominator is 1 minus x quantity squared, so we're going to wind up just getting 1 over 1 minus x quantity squared. And now what I want to do is take a look at what's going to happen at a particular x value. I'm just going to pick one that'll make our computing fairly easy. Let's take a look at f of, say, negative 1. This function should be defined there. We get negative 1 over 1 minus negative 1, which is negative 1 over 2. So our y value at negative 1 is negative 1/2. So, we're thinking about a graph where we have x value of negative 1 and a y value of negative 1/2. So negative 1 comma negative 1/2. There's a point there. We don't really know what else that curve looks like, but we know that there's a point there. Let's go ahead and see what's happening with the slope at that point. So if I wanted to find the slope at that point, I would use f prime of negative 1, which is going to be 1 over 1 minus negative 1 squared. I think you can see that's going to be, going to be 2 inside the parentheses, then it's going to get squared and become 4. So f prime of negative 1 is 1/4, which means that thing has kind of an instantaneous slope of 1/4. So it's kind of going up 1 and over 4 at that instant. Now, let's take a look at our inverse function. And because we know that f of negative 1 is negative 1/2, we should be able to predict that our inverse function, I'm going to call this guy g just to make our writing a little easier. We'll say g of x is x over x plus 1. We should figure out that g of negative 1/2 should equal negative 1. In other words, the x's and y's kind of get reversed. So let's see if that's actually true first. G of negative 1/2, we're going to put a negative 1/2 in for the x in the numerator, and then we're going to put a negative 1/2 in there in the denominator for that x, and we get negative 1/2 over positive 1/2. And that, of course, is negative 1. So it worked. So it looks like we have found the correct inverse function where we plugged negative 1 into the original function and got negative 1/2. Then when we took the inverse function, we plugged negative 1/2 in, and then we got negative 1. That's all well and good, but that's nothing that we couldn't have done in Algebra 2 or pre-calc. What we're curious about now is these slopes and their relationship. So we've already found out from our work over here that the slope of f at negative 1 is 1/4. And what I'm curious about is what's happening in g with its slope at the corresponding y value. In other words, what's happening with g prime at negative 1/2 and see if there's a relationship there. So first I'm going to have to find g prime of x. So I'm going to use quotient rule again. So it's low, d high minus high, d low, all over x plus 1 squared. And I think you can see it's going to be x plus 1 minus x over x plus 1 quantity squared, and we get 1 over x plus 1 squared. So that's g prime of x. So g prime of negative 1/2 is going to be 1 over negative 1/2 plus 1 squared. So that's going to be 1 over negative 1/2 plus 1 is negative, I'm sorry, 1/2, and once we square 1/2, we're going to get 1/4, and we get 1 over 1/4, and we get 4. Notice there is a little bit of a coincidence. I don't know if it's a coincidence or an actual real thing we've stumbled across. Look at the result. The derivative of the original function at negative 1 is 1/4, and the derivative of the inverse function at the corresponding y value is its reciprocal, 1 over 1/4, otherwise known as 4. And we're going to find that's not a coincidence, that's always true. And that's what we're talking about in this picture right here. If you have a function, this is the original function, let's say this is f of x, not this particular f of x that I was using it as an example, but just any old f of x that has a point a comma b, well, the slope at that point would be f prime of a, right there. So you take the derivative and plug in a, and that's going to give you the slope right there. Well, because this function up here is the inverse of f, it would have its curve, which would be a reflection over the line y equals x, and it would have the point b comma a. And so I'm saying right here at this point, where that guy would have f inverse's derivative at b, so this is why it's hard to do this. We're talking f inverse's derivatives. That's kind of a funky notation there. F inverse prime at b. That guy, talking about the slope of this line right here, is the same as the reciprocal of the original function's derivative at a. And there we go. That's roughly us saying, hey, f prime of negative 1 earlier was 1/4. That means g prime, its inverse, evaluated at negative 1/2, which is the y value associated with negative 1, is going to be the reciprocal of this guy's slope. So instead of 1/4, it's going to be 4. So that's a little bit of a thing, and it's not a coincidence. So here's how we're going to see this stuff play out sometimes come AP time. Take a look at example 2. Now I've kind of skipped this explanation because it's a little tedious, but we'll get some examples with this in class to kind of make sure that we're okay with that. But I think you'll wind up getting a better understanding of this stuff just to jump right into example 2. So we've got this quadratic, and they're telling us that x is greater than or equal to negative 1. And what that's going to do is make it so that our quadratic actually is invertible. Because, as you know, quadratics generally don't pass the horizontal line test. This thing, when x is negative 1, the y value is going to be 4. And then it's going to kind of come up like this. Now, of course, this function would go like this also over here. But if we're only talking about x's that are greater than 1, we're only going to be talking about this branch. So what I can do is come back and kind of eliminate that left side. So we're just going to take that part away, and now there's our function. So it kind of comes down and it just sits here and starts from there. But that's good news because now our function is invertible. But notice, they're asking us to find the derivative of the inverse function at x equals 8. Well, essentially what we did up here earlier, the top part of the paper, is we had a function, then we found its inverse, and we took the derivative of the inverse function. We could get whatever we want. However, this function with the x squared and a regular x, you can try it if you want, but good luck. If you're going to try to find the inverse of this function, you'd have to let y equals x squared plus 2x plus 5, and then switch your x's and y's, and then try to get y by itself. And I'm going to leave that up to you if you want to try it, but you're going to find out that it's not trivial. You're not going to be able to get y by itself very easily. It can be done, but it's not easy. And there are some times when, as far as I know, it couldn't be done. So what we're going to do is kind of use this reciprocal relationship. So since they want g prime at 8, I have to remember my relationship between functions and their inverses. If g has an x value of 8, let's say it's, I don't know, c, that means f of c equals 8. So in other words, if the inverse function has 8 comma c, the original function must have c comma 8. Well, what I could do is say, use this relationship, this new relationship that we have up here, and say that if I want to find g prime of 8, all I need to do is 1 over f prime at c. The problem is I got to figure out what c is. So c is the x value that I plug into f. C is the x value that I plug into f to get 8 as my answer. So let's go find out what that's going to be. So I'm going to use, I'll use c instead of x. C squared plus 2c plus 5 has to equal 8. And that's c squared plus 2c minus 3 equals 0, which factors nicely to c plus 3 and c minus 1. And so that's c equals negative 3 or 1. Now, negative 3 is not going to be for us because negative 3 is part of the function where we're not defined. So we got to cross him out. But at c equals 1, that's fine. So at c equals 1, we're right here, and we've got the point 1 comma 8. So what we can do is find out that the inverse function, maybe I can draw that in green, which would look, I don't know, something like this, is going to have a point here at 8 comma 1. And what I need is the slope of that guy. And luckily I have the clue right here. So what I need is to find out what f prime is. And f prime is easy enough. F prime of x is just 2x plus 2, just taking the derivative of this guy. So f prime of 8, I lied. I don't want f prime of 8. I want f prime of 2. No, I lied. 1. What am I thinking? F prime of 1 is 2 times 1 plus 2. So f prime of 1 is 4. So according to that, g prime of 8 is equal to 1 over f prime of 1, which is 1/4. So we were able to use our inverse slope relationship even though we never actually found the inverse function. We just used this kind of shortcut. So to kind of wrap up, we just have to think about when we're asked to find the derivative of an inverse function at a particular value, most times you're not going to have that inverse function. You're not going to have access to it either. You're not going to be able to go find it. So what you're going to be asked to do is find out where this x value of the inverse function, find out where it's a y value in the original function. And once you do that, you can find the x value that will give you that y value. And once you have that x value that gives you that initial y value over here, all you have to do is take the derivative of the original function, not the inverse, plug in that x value that you found, and then the answer you're looking for is the reciprocal of that. So like when you plug in, for example, 1 and we got 4, the derivative that they're looking for is the reciprocal of that 4, which is 1/4. Pretty common as an AP multiple choice question. We're going to get lots of practice on this, both in the homework, and I've got kind of like a worksheet that'll specialize in this stuff for you too. So that's going to wrap up kind of our first part of this thing, which has the relationship between a function and its inverse and their derivatives, how their derivatives or how their slopes are related to one another.